Can you see the screen?
Mm-hmm.
Okay, great.
All right, awesome. All right, let me introduce you. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Let me briefly introduce our speaker today. It is an honor to host Dr. Alberto Padovan, who is a postdoctoral researcher in the Department of Aerospace Engineering at the University of Illinois, Urbana-Champaign. He obtained his PhD from Princeton University in August 2022, and his research interests lie at the intersection of fluid mechanics, dynamical systems, and control theory. Alberto's current work focuses on the development of data-driven methods for model reduction of fluid flows, as well as on the analysis and control of supersonic and hypersonic wall-bounded flows. Today, Alberto will talk about data-driven model reduction via non-intrusive optimization of projection operators and reduced order dynamics. I'm sure we are going to hear a wonderful talk from him. Now let me ask a somewhat informal questions to Alberto just to get to know him better. Here we go. Are you ready, Alberto?
Ready.
All right. This is the best random question I came up with after hearing about your background. I happen to know you love soccer, and if you can share your favorite soccer player in history, not just
in history, favorite soccer player. I would say Paolo Maldini. He was the AC Milan captain. Yeah, so I'll go with him if I had to choose one. Yeah.
Do you have the reason?
Well, he was the captain of my favorite team for a long time, and I guess he's known as one of the best defenders to ever play the game. So
awesome.
That's why.
Very great. Okay. Stage is yours, Alberto.
What was that?
Stage is yours. It's your turn to give your presentation. Yeah.
Okay. Thank you, Dr. Choi, for inviting me at the DDPS seminar series. Today, I'll talk about data-driven model reduction via non-intrusive optimization of projection operators and reduced order dynamics. And here's the outline of my talk. I'll go over a few slides of introduction and motivation. I'm sure that most, if not all of you, are familiar with some of the concepts I'll be talking about. Then I'll go over an overview of some existing formulations. We'll touch upon Petrov-Galerkin models, which are intrusive, and then we'll talk about an existing non-intrusive formulation, which is known as operator inference. After that, I'll present the main topic of this presentation, which is Nitron. This is it's a non-intrusive trajectory-based optimization of reduced order models, and is an extension of existing methods that we've recently come up with. And then I'll show some examples. We have 3 examples of increasing complexity: a toy model, a one-dimensional PDE, and then a 2-dimensional lid-driven cavity flow. Okay, so even though I'm sure that most of you are familiar with the overarching idea of model reduction, I thought it'd be good to set some foundations just in case. And so physical systems that we're interested in studying or simulating, like fluids or solids, are described by partial differential equations. And after spatial discretization, we obtain systems of ODEs with many degrees of freedom. So here's a brief example. We have the incompressible Navier-Stokes equations. And after spatial discretization using finite difference, finite volume, finite element, you name it, your favorite spatial discretization scheme, we obtain a system of ODEs where here, for instance, U sub d is the velocity on a mesh, and PD is the pressure, and Q is the spatially discretized state. And so the main challenge associated with this high dimensionality is computational cost, and this can come in many flavors, but Most notably, one is the cost associated with integrating equation 1 in time. And number 2 could be related to the cursor dimensionality during tasks such as optimization, control design, and system analysis. So to reduce cost, we'd like to find a reduced order model, which is a system given in equation 2 that behaves like equation 1 in some sense, but it's much cheaper to work with. And the reason why it's cheaper to work with is because the reduced order model state Z has dimension that is usually much lower than the dimension of Q, so we can integrate and work with equation 2 in a more computationally efficient manner. All right, so there are many approaches and many decades of literature on model reduction for physical systems, but most of them tend to share this type of architecture that I'll discuss in a second. So the first step is we start from what we call the full order model, or the FOM. This is the spatially discretized Navier-Stokes equations. If you're working with fluids, Q is the state vector. It could be the velocity, density, or any flow variable you're interested in. And U, in case there's a control input, for instance, could be a boundary forcing, a volumetric forcing, whatever type of actuator control input you might have on your system. And so a reduced order model can be described schematically as follows. We have 3 components. We have an encoder, a decoder, and ROM dynamics. So the decoder psi is a possibly nonlinear function that takes you from the high-dimensional space onto a low-dimensional space. This could be a linear subspace or a nonlinear manifold. And so basically this operation is that of a compression. So we'll go from high dimension to low dimension. Once we're in low dimensions, we have the ROM dynamics that evolve the low-dimensional state in time. And then finally, we have a decoder, which is a possibly nonlinear map from the low-dimensional space to the high-dimensional space, and gives us this quantity Q hat, which is the approximate solution Q. And hopefully, once we've gone through this pipeline, Q hat is not so far away from the ground truth solution Q. And as I was saying, there are many different approaches to this and decades of literature. So the encoder and decoder, it could be linear, it could be nonlinear. The encoder and decoder could be constrained to define a projection. So where, for instance, the encoder is a left inverse of the decoder, and so we are implicitly defining a projection. And then also it could be intrusive or non-intrusive in the sense that the computations that give us phi and psi could be relying on the full order model, or it could be relying exclusively on data without any knowledge of the governing equations that generated the data itself. And then as far as the ROM dynamics go, we could have continuous time dynamics, discrete time dynamics, and again, they could be computed intrusively or non-intrusively, depending on the specific application. All right, so on today's talk, we're going to constrain ourselves to encoder and decoders that are linear, so they can be represented as n by r matrices in this specific case. Also, we constrain them to define a linear projection. So here you see that the encoder is a left inverse of the decoder by design. And then also the reduced order model dynamics are continuous in time. And so today's overarching question is, how do we learn phi, psi, and the ROM dynamics G non-intrusively with the additional constraint that phi and psi define an oblique projection? All right, so why do we insist on projections in the first place? So as I said before, if the encoder is the left inverse of the decoder, then we're implicitly defining a projection operator, which I call P. And if phi is equal to psi, then the projection is orthogonal, and if they're not equal, then the projection is oblique. So here's a schematic of what an orthogonal and oblique projections do. So if we have a 3-dimensional vector Q in 3-dimensional space, and we have a target subspace, which is the span of phi, then an orthogonal projection will basically take Q and project it onto phi in the direction of the orthogonal complement of phi. But if we want to have an oblique projection instead, we need an additional component, which is another subspace psi. I'm sorry, another subspace which is given by the span of psi. And so the oblique projection will take the vector Q and project it onto the span of phi along the orthogonal complement of the span of psi. And so in general, we like projections because if the vector Q lies in the range of the projection, then basically the projection operator P is effectively the identity operator on its range. And so intuitively speaking, and from the physical standpoint, this means that the operation of encoding and decoding the FOM state does not introduce a spurious drift in the ROM state. So basically what we're saying, if the ROM dynamic, if the reduced order model state is evolving, we want it to be evolving because of the ROM dynamics, not because of the operation of encoding and decoding going from high dimensional to low dimensional space. So this is, loosely speaking, the reason why we like projections. Now, why do we like oblique projections? So there's many reasons why we, going over all the reasons why it would take a lot of time. But in general, we need oblique projections for systems that are commonly referred to as non-normal. And so where, loosely speaking, low energy states that we might not be able to see in a simulation are nonetheless dynamically important. And so to capture those types of mechanisms, we need oblique projections. So I thought I'd give you an example of the reason why oblique projections are good. So this is not quite an explanation of why we need them, but more so evidence of the fact that we do need them. So as a simple example here, we have the complex Ginzburg-Landau equation. We'll go back to a description of it in a little bit, but for now, the important thing is that we have a 1D PDE, and we'd like to be able to compute reduced order models that are that can predict the time history of the output y in response to some input u. And so that's the name of the game. So instead of solving this PDE, we want, in this specific case, 5-dimensional reduced order models that can tell us what happens to y as we force the system with some unseen input u. And so I'll try to unpack this figure as best I can. So what we did here is we forced equation 4 with an impulse. So we started from a non-zero initial condition in the span of b at initial time, and then we let the simulation go and we compute y. And so the ground truth history of the output y is given by the black line. And then what we do here is we use 4 different model reduction approaches to compute 5-dimensional reduced order models. And I'll describe each one of them in detail in a little bit, but for now, the important thing is the following. So we have the first 2 methods are, one is intrusive and the other one is non-intrusive, but the important thing is that they both rely on orthogonal projections onto a low-dimensional subspace. The bottom 2 are, one is intrusive, the other one is non-intrusive, and it's the one I'll be talking about mostly today. But the most important thing is that they compress the data using oblique projections. And you see the striking difference between the predictive capabilities of models that use oblique projections over models that use orthogonal projections. Both models using oblique projections are doing a great job at tracking the ground truth history of the output, whereas the models that rely on orthogonal projections are not doing that great a job. And this is also true for a different type of input. We're forcing with a sinusoid now, but the picture remains qualitatively the same in the sense that oblique projection ROMs are doing a good job at tracking the output, whereas orthogonal projection ROMs are not really giving us good prediction of what happens to y in response to u. All right, so I hope this was, I guess, convincing evidence enough of the reason why we need oblique projections for model reduction. So here's an overview of some existing formulations. So perhaps the most well-known approach to obtain a reduced order model is Petrov-Galerkin. And so this is an intrusive approach, and computing the reduced order model requires knowledge and access to the full order governing equations. And so if we have if the FOM equations are given by equation 5, this again could be the spatially discretized Navier-Stokes equations. Then the Petrov-Galerkin dynamics are given by equation 6. And what equation 6 is telling us is that we are constraining the state Q to the range of the projection for all times. And also, not only are we projecting the state onto the range of P, but we're also projecting the dynamics F onto the range of P. And so we obtain this model that is to be designed in such a way that Q hat is as close as possible to the original state Q. And so even though the state Q hat in this specific, the way I've written it has the same dimension of the state Q, the dynamics in 6 can be realized by a low dimensional system where the dimension of the state Z is that of the rank of the projection. And so we see that basically the takeaway from this slide is that Petrov-Galerkin model, the degrees of freedom in Petrov-Galerkin model. So what we get to choose are the matrices phi and psi. But once we choose those, the Rom dynamics are fully determined by phi psi and by the full order dynamics F. I would like to point out that actually we don't need to specify phi and psi more so as their span. So really, a Petrov-Galerkin model is not a function of the matrices phi and psi, but rather a function of the spaces that they span. And we'll come back to that in a little bit. So the question is, how do we pick phi and psi? There are different ways to do that. Perhaps the most popular one is POD. POD-Galerkin is a weakly intrusive approach, and it's historically the simplest way to choose phi and psi. In fact, it goes like this. We collect data from a full order simulation, we stack it into a matrix, and we take its SVD. Then what we do is we retain the first R columns of U. We call these the leading R POD modes. And then we simply set phi equal to psi equal to the first R POD modes. Once we have phi, we can easily compute the Rom dynamics as shown in bullet point 3. And so this implicitly defines an orthogonal projection onto the range of the POD modes. And the Rom is known as a Galerkin model. And so from an intuitive standpoint, what we're doing here is we are projecting the governing equations onto the span of the most energetic features of the system. However, as I discussed briefly a few minutes ago, there might be non-energetic states that are dynamically relevant. So that's when we need oblique projections. And so a common way to get an oblique projection is balanced truncation. And so it was first developed in 1981, so it's a somewhat old formulation, and it's a tool from linear control theory. And the method is highly intrusive, and I'll describe it in a minute what I mean by it. And so balanced truncation proceeds as follows. We start from the nonlinear governing equations, and the first step is we need to linearize about a fixed point. And so here A is the linearization of F, is the derivative of F with respect to the state, and the input matrix B is the derivative of F with respect to the control input. And so now we've obtained a linear time invariant system which we can work with. We like LTI systems because we kind of know everything there is to know about LTI systems, and we can work with them pretty easily. And so the name of the game in balanced truncation is the following. We want to find and truncate a set of coordinates where the controllability and observability gradients are equal and diagonal. Now, the specific details are not important, but basically to find phi and psi, we need to compute these integrals in the parentheses. And you see that these integrals, which are the gradients, depend on A and A star, which is the adjoint of A. And so in that sense, this method is very intrusive because we cannot treat the solver as a black box. We have to go into the solver, we have to linearize it, and then we have to compute its adjoint. So those are very intrusive operations. In any case, once we have phi and psi, we can go back to our nonlinear system, and we can obtain a Petrov-Galerkin representation of it as follows. So as I was saying, this method is very intrusive because not only do we need to query F to compute Rom dynamics, but we also need to access the linearization and its adjoint around a steady state. So that's an intrusive operation. The third approach I'll be discussing today really briefly is a novel formulation that we developed a couple of years ago, and it's called TROOP. It's trajectory-based optimization of oblique projections, and it produces a ROM as follows. The actual concept is pretty straightforward. We collect trajectory data and we save it from a full order simulation. And then what we want to do is we want to find subspaces V and W that define an oblique projection that minimize this cost function, which is just the mean square error between the ground truth data and the Rom prediction, subject to a Petrov-Galerkin model of this form. So remember that, as I said before, an oblique projection is not really a function of phi and psi, but it's a function of the subspaces V and W that they span. So the optimization problem is carried out in terms of these subspaces, and the appropriate optimization space is the Grassmann manifold. And we'll come back to that in a second once we discuss nitron. But the takeaway from this is an extremely intrusive procedure. So if you want to compute the gradient of the cost function with respect to the subspaces, then you can sort of see how we'll have to compute the linearization of f and its adjoint along entire trajectories. So the reduced order model is a function of phi and psi, but these phi and psi are fed into the CFD solver. So if you want to compute gradients, we'll have to differentiate the CFD solver, and that's extremely intrusive. Okay, so enough with intrusive methods. We'll move on to one non-intrusive formulation, which is operator inference, which is very much related to nitron, as we'll see in a second. So I'll provide a brief description of it here. So as we were saying, in Petrov-Galerki models, the only thing that we can choose are phi and psi. And then the ROM dynamics G are tied to the form dynamics F. In purely data-driven methods, we can also choose G. As a matter of fact, we're forced to, because data is the only thing that we have to back out G. We cannot really access the governing equations. And so operator inference proceeds as follows. The first step is we collect data from a representative trajectory, and we do POD, and we let phi be equal to psi equal to the POD mode. So we're implicitly defining, we're compressing the data from a high-dimensional space to the low-dimensional space via orthogonal projection onto the span of POD modes. And so the second step is the following. Well, as I just said, we compress the data onto the span of POD modes, and we get coefficients Z. But we also want to get the coefficients. We also want to get the time rate of change of those coefficients. So we take the time derivative of the full order state, and we project it onto the span of the POD modes. And so, assuming that the reduced order dynamics are polynomially formed, so they can be written as in this equation here, operator inference solves this least squares problem, where basically we want to find reduced order tensors A, H, B, and however many others that minimize the difference between the ROM dynamics and the time rate of change of the projection of the form state onto the POD modes on the span of the POD modes. So basically, in operator inference, we set the encoder decoder to be given by the POD modes that defines an orthogonal projection, and on the span of those modes, we want to find polynomial dynamics by fitting tensors. Okay, great. So this is kind of the overview of the methods that are inherently connected with nitron, which I'll be talking about in a second. I'd like to point out that there are many different other ways to do model reduction. As I said in the introduction, discrete time dynamics, nonlinear encoder decoders. But as far as we're concerned today, this is what we will be comparing nitron against. So here we go. So this is non-intrusive trajectory-based optimization of reduced order models. And this method kind of brings together concepts both from intrusive models and from operator inference. But the beauty of it is that we will not need access to the governing equations, and we can do the optimization purely from data. And so, loosely speaking, is what we do is we simultaneously, non-intrusively look for optimal phi, psi, and G given full order trajectories. And so this is the full order model. Here, again, this could be any spatially discretized PDE. We have an initial condition Q naught. And then also, we might be interested in some observable Y. This could be pressure at a wall, it could be shear stress, it could be the velocity profile somewhere on your computational grid. And then what we're looking for are reduced order models of this form. So we have the dynamics of the ROM evolving the coefficients on the span of a projection that will be defined shortly. The initial condition is the projection of the initial condition of the form onto the span of phi. And then we have the predicted output y hat. And so a couple of things I want to discuss a couple of things before we lay down the optimization problem in mathematical terms. The first thing that we observe is that the ROM is not a function of phi itself; is a function of the subspace that's spanned by phi. And so, in fact, it can be shown that for any invertible matrix M of size R by R, this relationship holds. This means that if we stretch and rotate phi, we're not changing the reduced order model. So r-dimensional subspaces of Rn are elements of the Grassmann manifold, and so we'll be looking for an optimal V on the Grassmann manifold. A similar symmetry does not hold for psi. In fact, there exist invertible R by R matrices M where this equality doesn't hold. So meaning that if we rotate and stretch psi, we do change the reduced order model. And so the ROM is not a function of the span of psi, but rather a function of psi itself. Nonetheless, we want psi to have rank R, otherwise we wouldn't be able to define a projection. And so without loss of generality, we can take psi to be an element of the Stiefel manifold, which is the space of orthonormal n by R matrices. And the third assumption, the assumption we make next on the ROM dynamics is that they are polynomial. And so we're kind of borrowing this from operator inference that we described a minute ago. And so, yeah, we're saying the polynomial dynamics are polynomial, the ROM dynamics are polynomial. So the parameters we'll have to learn from data are these tensors A, H, and B in red. So altogether, the red quantities on this slide are the ones we'll try to fit from data. Okay, so mathematically, this is the optimization problem. So we have ground truth observations from the FOM called Y, collected at some temporal instances Ti, and then we have a reduced order model of polynomial form that will give us a prediction Y hat at the same times. And what we want to do is we want to minimize this cost function by choosing a subspace V on the Grassmann manifold, a n by R matrix psi on the Stiefel manifold, and reduced order tensors that define the dynamics. And so the optimization is carried out on this product manifold of the Grassmann, Stiefel, and as many linear spaces as the number of tensors that we're trying to fit from data. Okay, so how do we compute the gradient? So the trick is that this manifold M that we've just defined, maybe it's best if I go back, it's an abstract manifold. It's abstract in the sense that the Grassmann is a manifold of subspaces, and subspaces are abstract entities that we cannot represent on a computer. The only way we can represent subspace V on a computer is indirectly through phi, and then V is equal to the range of phi. So how do we deal with this abstraction? The way to do it is to work to view the Stiefel and the Grassmann manifolds as submanifolds of an ambient space whose elements can be represented easily on a computer. So Stiefel can be viewed as an embedded submanifold of Euclidean space of matrices of size n by R. And then if we define a metric on this space, the Stiefel manifold will inherit it. And the Grassmann manifold can be viewed as a quotient manifold of the non-orthogonal Stiefel manifold. So this is the space of n by R matrices of rank R. And so again, if we define a metric on this space, then the Grassmann manifold will inherit it. Once we've done that, it is possible to define the gradient of the cost function in terms of Euclidean space objects. So, for instance, we can define the gradient of the cost function with respect to the subspace V in terms of phi, and so we can easily compute that on a computer. And so the approach is quite standard. We have our cost. We use the method of Lagrange multipliers with our cost function. We append the constraints, and here lambda are the Lagrange multipliers. It can be shown that these satisfy reduced order adjoint equations, and then once we turn the crank on calculus variations, it can be shown that the gradient of the cost function with respect to the parameters can be computed in closed form. So, for instance, just to give you a sense of what this might look like, the gradient of L with respect to A looks like this, right? And so you can think of, and the procedure that gives you the gradient is it's very much akin to a back propagation when you're training neural networks. I guess the beauty of the way we laid out the problem is that the gradient of our quote unquote neural network it can be computed in closed form, and so we don't need automatic differentiation to carry out this optimization. All right, so I guess it's time for some results now, and we'll look at 3 different examples: toy model, a 1D PDE, and a lid-driven cavity flow. So the toy model is a system of 3 ODEs. It's a very simple system. We state x1, x2, and x3. We have an input u, and what we're interested in is the time history of the output y in response to inputs u. This nu here is a parameter that we've introduced to show the need for oblique projections versus orthogonal projections. So if nu is very small, or even equal to 0 for the sake of the discussion, the dynamics become effectively linear, but most importantly, they are governed by a diagonal linear operator. A diagonal operator is normal, and so we expect that model reduction approaches that rely on orthogonal projections will give us good reduced order models. Instead, if nu is large, the system is nonlinear, but more importantly, this nonlinearity has a special feature. So we see that it depends on x3, and so if you look at what x3 does, x3 is the fastest decaying state of the system. So it decays, well, its dynamics are linear, and it decays with rate -5. And so this x3 is the least energetic state of the system, but nonetheless, it has a very large effect on the dynamics of x1 and x2. And so if nu is large, of course. And so if nu is large, we expect that we're going to need oblique projections for model reduction, because oblique projections give us the possibility of detecting the fact that low energy states might be very important from a dynamical standpoint. Okay, so we consider 2 different cases, nu equal to 5 and nu equal to 20, and we train the models with 4 step responses. So we have a step input u, we put it into the dynamics, and then we collect the time history of y in response to these four steps. Just to be clear, we're not computing a parametric ROM as a function of nu. We're considering 2 separate cases just to show when you may or may not need oblique projections for model reduction. So here we're showing the average testing error across 100 step responses for nu equal to 5, and here for nu equal to 20. So we see that for nu equal to 5, we've seen that the dynamics are effectively linear and normal. So all model reduction approaches, including those that use orthogonal projections, namely POD galerking and operator inference, are doing pretty well. The error is very low, and even though we're improving on it with our formulation, there's really no need for oblique projections in this specific case. But if we turn up the value of nu, then the dynamics become more quote unquote non-normal, where this low energy state is becoming more dynamically important. And we see that the 2 model reduction formulations that leverage oblique projections are performing significantly better than orthogonal projection-based reduced order models. And so these are plots that are computed using step responses. This is what we trained on. But what about different types of inputs? So here we put in sinusoids. And so we didn't train on sinusoids, and we hope that our training has given us models that are capable of telling us what happens in response to a different type of input that we haven't seen before. And so if nu is small again, and the dynamics are effectively normal, we see that all model reduction formulations are doing extremely well. There's no distinction between them, at least from a qualitative standpoint. But then if we turn up the value of nu, we start seeing some major discrepancies, and we see that Troop and Nitron that rely on oblique projections are tracking the ground truth output very well, but the other 2 formulations are not doing so good a job, as it can be seen from this figure. Okay, so this is all for the reduced order model. We'll move on to a more complicated system. You've already seen this briefly in the introductory section of the talk. So this is the complex Ginzburg-Landau equation. So this is a 1-dimensional PDE, and where here nu, gamma, and mu, and a are parameters. We choose them so that the origin is linearly stable. The system, however, despite the fact that it's stable, it will exhibit large amplitude transient growth. And this is due to the fact that the linear operator here is non-normal. And so again, this is one of those instances where we'll need, whether we work intrusively or non-intrusively, we need to compress the data using oblique projections. And so just for the sake of example, what we'd like to do is to be able to predict outputs y in response to inputs bu. And so here in this figure, I'm showing the spatial distribution of the input and output operators b and c. Here we have b in black and c in red. And so from a physical standpoint, we're forcing the system upstream, and we're observing the response downstream, and this is typical of spatially developing flows. For instance, where take a jet, for instance, where you might actuate near the nozzle, but then you want to look at what happens to vorticity downstream. And so this is kind of what we're trying to emulate here in this example. And we look for models with dimension 5, and we train with 4 impulse responses. So the spatial distribution of the impulse is in the span of b. What we vary is the amplitude of the impulse magnitude u at time 0. And so once we train, then we test across 25 impulse responses with unseen amplitudes. And here we have, again, POD-Galerking, operator inference, troop, and our formulation nitrom. And we see that nitrom and troop, for that matter, are doing very well, and they're maintaining a very low average error across time. And here on the right-hand side is a representative trajectory of the output y taken from one of these impulses that we tested on. And so we see that both troop and nitrom are capable of tracking the ground truth time history of the output y, but the other 2 formulations with orthogonal projections are not really capable of giving us a faithful prediction of what happens to the full order system in response to the input. And then just to make sure that we've learned dynamics and we haven't overfit impulses, we change the forcing input. On the left-hand side, we're forcing with a sinusoidal input with frequency omega. This is roughly the natural frequency of the full order dynamics. And we see that we're tracking the output pretty well. And this is the analog for the second harmonic of the fundamental frequency. And again, we see that we're doing a pretty good job here as well. You can see some minor discrepancies here at later time. This is probably due to the fact that the frequency content 2 omega wasn't that dominant in the training data set. So the model hasn't really seen a lot of 2 omega structures showing up in the training data set. So I guess that the forcings with frequency 2 omega are somewhat out of distribution for, nonetheless, we're performing much better than the other methods using orthogonal projections, and much better than operator inference, which is non-intrusive. Okay, so this is the last example I'll be talking about. So this is I guess the highest degree of complexity we've considered. This is a 2-dimensional incompressible lid-driven cavity flow at Reynolds number 8300. The top boundary of the domain moves with horizontal velocity u equal to 1, and we spatially discretize the Navier-Stokes equations with a finite difference scheme on a 100 by 100 grid. So what we want to do here, for the sake of example, we want models that are capable of predicting the whole velocity field, so the whole u and v velocity field on the whole domain, in response to inputs that enter the flow via spatially localized body force that is placed near the top right corner. So you can envision this as being like a Gaussian spatial profile that injects that acts as a body force on the momentum equation of the fluid. So what we do is we train reduced order models of dimension 50 with 7 impulse responses. And just to give you a sense for how this flow behaves, I've plotted the energy of the perturbation from the training trajectories over time. And what I mean by perturbations, these are fluctuations about the steady state that exists at Reynolds number 8300. And so most notably, what happens here is that after an initial decay in energy, the energy spikes back up at roughly at time equals 5 or 6. And this is typical behavior of non-normal systems where there's transient energy growth. And in this specific case, it's pretty high amplitude. If the system was normal, then the energy wouldn't spike back up, and it would keep on decaying back to 0. And also, I'd like to point out that this figure also indicates that the system is quite nonlinear, because these lines are not scalar multiples of each other. So if the dynamics were linear, then these would be scalar multiples of each other, but they're not in this case. So we're looking at a nonlinear system that has underlying non-normal like dynamics. All right, so we do not apply troop in this specific case because it's very intrusive, but what we consider is Petrov-Galerkin projection, operator inference, and nitron. And so this is the training error for the 7 training trajectories we considered, and this is the testing error for unseen impulses. And we see that with nitron, we've managed to keep the error pretty low, even at times before 10, where we have that huge spike in energy in the training trajectories and testing trajectories for that matter. So the question we're asking next is, okay, we have a model that performs pretty well on impulses. How does it perform on unseen inputs? And so, as before, we force the system sinusoidally. And so we have 6 different runs, and we consider harmonics of the frequency 1.25 and harmonics of the frequency 1. These are frequencies that are relevant for the full order dynamics. And we see that in all settings, we're doing a really good job at tracking the energy, the evolution of the energy of the perturbations for, as I said, for all scenarios. In particular, I want to point out that at long time, aside from perhaps minor discrepancies in amplitude, we're getting the right phase of these oscillations, and also at early times we're doing very well at tracking the initial growth of energy before the system settles onto a forced limit cycle. And so this is what snapshots from these solutions look like. We have top left the full order model. This is the ground truth solution computed from CFD. This is nitron. Again, these are 50-dimensional models. Operator inference and POD Galerkin. You see that POD Galerkin and operator inference are underestimating the magnitude of the vorticity that arises in response to these sinusoidal inputs, but also they're not predicting the phase correctly. So if you look at this blue vortical structure here at x equal to 0.5 at the bottom of the cavity, you see that operator inference and POD Galerkin predict structures that are out of phase with that structure. By contrast, nitron is doing a very good job at predicting both the amplitude of the vorticity field and the phase of the vortical structures. And here's another set of snapshots for a low frequency forcing input in this case. Again, nitron is capable of predicting, giving a good prediction of what happens to the flow. By contrast, operator inference and POD Galerkin are they seem to be overestimating the vortical structure, the magnitude of the vorticity, and they are not giving a faithful representation of the type of vortical structures that we see in response to the input. Okay, so in conclusion, we have introduced a novel, non-intrusive model reduction framework for systems that exhibit large amplitude transient growth. And the key takeaway is that we improve on existing non-intrusive methods by projecting the high-dimensional data onto low-dimensional subspace via oblique projection. And that's the key. The improvement here is that we're capable of computing oblique projections directly from data for model reduction. Future work, here we're considering linear projections onto linear subspaces, but it would be interesting to extend the formulation to nonlinear projections onto polynomial manifolds, and it would be fascinating to be able to do so while keeping while still being able to compute the gradient in closed form. And we'll have to see if we're able to do that without relying on automatic differentiation. Yeah, so I'd like to acknowledge the contributions from my collaborators and co-authors, Blaine Vollmer and Professor Bodoni at UIUC, and Professor Bodoni is my postdoc supervisor, and then of course funding from the National Science Foundation. Okay, well, thank you for listening, and I'm very happy to take any questions.
Thank you so much for the wonderful talk, Alberto.
Yeah.
Great job. Okay, let's have a Q&A sessions. We do have a question from the chat. Kevin asked, thanks for the talk. It was very interesting. Can you give us a more insight explanation on how oblique projection performs better than orthogonal projection?
Right, yeah. So let me see if I can perhaps. Okay, so I'm trying to give an answer from a physical but also mathematical standpoint. So typically when we do orthogonal projections, we look at POD and we use POD to do so. And POD will take trajectories and look and will give you a projection onto the features that are most energetic. So for instance, in this simple toy model, POD would tell you that the most energetic states are x1 and x2. And so we'd be performing, and we'd be projecting, the reduced order model would be neglecting the state x3. The trouble with that is that the state x3, even though is very low energy because it decays very fast, it's extremely dynamically important because we see that x3 has a large impact on the energetic structures. So we have a situation where we have high energy structures, but their dynamics is very much affected by low energy structures that procedures like POD would completely disregard. So what an oblique projection lets you do is it lets you identify the high energy subspace, so that it will give you phi, high energy subspace, but it also gives you the possibility of choosing psi. And psi can be chosen in such a way that it accounts for the fact that x3 is dynamically important. So when you have an oblique projection, you have more degrees of freedom, if you will. You have the subspace where you project onto, but you also have a subspace that tells you the direction along which to project. And so by doing that, you're capable of that's loosely speaking why oblique projection operators tend to work better than orthogonal projection operators. Yeah.
All right, thank you. Next question is by Giselle. Why is the error consistently higher near t is equal to 0, for example, for slide 27 across the board? Can you go to slide 27? Is this due to the increased complexity of the function at earlier times, which diminishes later, or is there another factor contributing to this behavior that I might be missing?
Right.
What happens with where am I? What happens with these models if you extrapolate to times that your model hasn't seen?
Right. Yeah. So there's two questions there, I guess. The first one is, why is the error consistently higher at early times? Okay. So basically, oblique in general. Okay. So most of the contribution to the cost function error is due to the long time dynamics of the system. So for instance, if you have a limit cycle, for example, a good reduced order model will be a model that gives you the correct amplitude of the limit cycle oscillations and the correct phase. And so in order to do that, it might not be necessary to minimize the error at early times. What's important is that the ROM trajectory is in the correct phase with the FOM trajectory once the FOM enters the low dimensional subspace. So basically, it's kind of a feature. It's kind of something that we have to live with. Like the initial condition that we are looking at might not be close to the subspace that we're projecting that we're using for model reduction. And we're okay with that. What oblique projections allow us to do is that over time, the ROM trajectory and the FOM trajectory will approach each other and will continue in a synchronized fashion. And at that point, the ROM will be very good and the error will be very low. So that's kind of early time errors is kind of something that there's not much we can do about, because the initial condition might be far away from the low dimensional subspace that we're considering for model reduction. So I hope that answers the question. Second question that we had was
Extrapolation.
how does the model perform for long times? It performs very well, I guess. So in this case, for the toy model, we've trained from 0 to 10, but we're testing the sinusoidal input is carried out for 30 time units. So it's 3 times the temporal extension of the, it's like 3 times the length of the training data set. And the same goes for the complex Ginzburg-Landau equation and the lid-driven cavity flow. We would hope that it's kind of a it's important that models are able to extrapolate in time, and the way to guarantee that is to make sure that we're actually learning good dynamics, and that we're not, of course, overfitting. Once we're confident that the ROM that the ROM dynamics and the projection is good, then we tend to observe that the model is very capable of extrapolating to very long times that hadn't been seen before. Yeah.
Awesome. Well, follow on to that. I mean, your examples are statistically periodic or the deterministically periodic, right? If you are extrapolating time domains, you have seen those data before. So you are able to capture that using the subspace you trained with the oblique projections and the operator inference framework.
Yeah, I'd like to point out that yes and no. No, in the sense that we don't train on periodic data, we train on impulses, right? So the type of, although the information contained within those impulses is enough, that the model figures out that if you force sinusoidally, you will induce a limit cycle and with a certain frequency and amplitude. And so that's why it's capable of giving good predictions for a long time. Yeah. So yeah, I agree. Like the model is at the end of the day, as in with for any other data-driven method, if the input is in distribution, then we expect it to do well. If for some reason we have inputs that had no signature on the training data, then the model might fail.
Yeah. Totally agree. Any other question? I have a couple of questions. So, all right. So before I go to my question, yes, Federico asked 2 questions. He said, very interesting talk. His first question is, do you have a qualitative estimate of the time saving of nitro ROM compared to the FOM in the example? So basically speed up he's talking about.
Right.
And second question is, which criterion did you use to decide the dimension of the reduced model basis dimension of 50?
Great question.
For the last example, I guess.
Yeah. Well, okay. So as far as speed up goes, I haven't computed it, but for this example, we have okay. So this would be 2 flow variables. It would be 20,000 dimensional, if I'm not mistaken. And so 20,000 degrees of freedom versus 50. I don't know. You do the math, like 1,000 times faster, roughly, depending on. Yeah, it's quite a bit faster. As far as the other, okay, how did you pick the dimension? Okay, so I picked the dimension by doing POD first and looking at the decay of the singular values of the training data set. And the leading 50 modes gave us, forget, like roughly 99% of the total variance in the data. So that's a very common criterion to pick the underlying ROM dimension. Yeah.
All right. Thank you. Gizel asks, does it make sense to test this approach on chaotic equations such as the Lorentz system?
That's a fantastic question. There might be a little bit of difficulties with that in that, okay, let's see. It might make sense to do it. I would actually be very curious to see what happens, but one needs to be careful when computing the gradient, right? Because when we're integrating the ROM adjunct equation in time, so effectively we're back propagating the error through the trajectories. If the system is chaotic, then the gradient will blow up. There are, I'm not too familiar with literature on how to handle that, but I know there are ways to optimize systems, in the presence of chaos. So one might need to do a little bit of trickery to be able to carry out the optimization. But in principle, yes, I would believe that it would make sense to look to apply this formulation to chaotic systems. Yeah. Thank you for the question.
Thank you. So going back to my questions, my first question is kind of related to what Gizel asked earlier about, earlier times you got higher error and, for example, the lead-driven cavity problems. It clearly has a high energy phase, and later on that energy dies out. So there, for the particular problem, if I have to divide the simulation into two phases, there's a early phase and later phase. There's the concept called the time windowing ROM, where you can, come up with a different set of the basis for different phase. So in the beginning phase, you tailor your basis so that it can capture the high energy better, and then later on it's easier problem, so you probably get away with the smaller dimension of the basis. So I think you could extend your algorithm to time windowing framework to even further improve this high the relative error in the early time phase.
Yeah, that's very interesting thought. Yeah, so I guess that that approach would let us maybe decrease the initial error due to the fact that the initial condition is far away from the subspace we're projecting onto, but then we move on to a different subspace later on in time. That's a great thought.
And I mean, there's more discussions onto it, but yes, that's the basic idea. And when you go from one phase to the another phase, you could come up with some sort of physics indicator depending on the applications, so that indicator tells you automatically where to change from first phase to the second phase. Suppose we don't want to manually cut at this time. Yes. So my second question is, okay, you have presented in the context of the reproductive case only, and natural next step would be the parameterization, like the generalization of your method. If you can share any thoughts on that, because that's natural next step.
Right. Yeah, so if we want to have parametric reduced order models, I guess that if I had to think about it really quick, how to do it would be to interpolate across in parameter space, and of course we'd have to be careful about how we do that, because we're like at each parameter where we actually perform a fit, we are computing subspaces and elements of Stiefel manifold. And so we'd have to interpolate on those manifolds, and also we'd have to guarantee that the interpolated once we interpolate, we preserve the property that phi and psi define a projection. Yeah, so I guess that those would be the first concerns. Yeah, but yeah, it's very much next step on how to extend it, and I welcome any sort of input. You guys are all experts in these topics. Yeah.
So there is a interpolation in Stiefel manifolds. There's a technique for that. So I can definitely share that with you. But yeah, totally agree. You know, interpolation would be a way to go for the parameterizations.
Right.
Awesome. Okay. All right. Is there any other question?
Okay.
If not, let's thank our speaker for the wonderful talk. Thank you so much, Alberto.
Thank you so much. Thank you for joining.
Very nice work. And after this talk, hopefully there will be more collaboration between Lawrence Livermore and your
I would love that. Let's keep in touch.
All right. Sounds good.
Okay. Thanks for having me again. Bye-bye.
Thank you. Bye.